Hi everybody, I'm Daniel Fejgin from University of Oldenburg, and together with Simon Doclo, we wish to cordially welcome you to our presentation. After this talk, you should take home 1. How we estimate the direction of arrival, the DUA, of a target speaker in a reverberant acoustic environment with diffuse noise using binaural hearing aids in conjunction with an external microphone. 2. The suitability of the frequency averaged emission angle as a cost function for DUA estimation, incorporating so-called relative transfer function vectors, or RTF vectors for short, of the head-mounted microphones. 3. You will see how different RTF vector estimation methods perform in terms of their DUA estimation accuracy. And 4, you should take home how an external microphone, which is not restricted to be worn by the target speaker and that has an unknown location, and that can in principle even move around freely in the room, can aid to localize a speaker in such a binaural hearing aid application. So stay tuned and enjoy. Our main goal, the estimation of the target speaker DUA, is achieved in this last block, where the head-mounted RTF vector estimate is compared against the database of prototype unequivocal RTF vectors for different discrete directions. These head-mounted RTF vectors, they're estimated in the middle block here, and we will consider 3 different estimation methods. Also, the RTF methods, they rely on estimates of covariance matrices, and therefore in the first stage of this processing pipeline, we will need to estimate the covariance matrices of the speech plus noise components and the noise components, or only the covariance matrices of the speech plus noise component. Depends on the respective RTF estimation methods. In the following, we will have a closer look on these blocks, how to estimate the RTF and the direction of arrival. As pointed out, opposed to other popular DUA estimation approaches that make use of interchannel time and level differences, generalized cross-correlation features, or subspace methods like music, we approach the binaural DUA estimation task using head-mounted RTF vectors. These head-mounted RTF vectors, they encode the source DUA, but they obviously do not depend on the position of the external microphone, as they contain only the relative transfer functions of the head-mounted microphones. This should not be misunderstood that one cannot make use of an external microphone to anyway estimate the head-mounted RTF vector. So that is why we stress, in addition to the head-mounted microphones, an external microphone can be employed and is employed to estimate the head-mounted RTF vector. To estimate the head-mounted RTF vector, we make use of state-of-the-art covariance subtraction and covariance widening, as well as the recently proposed spatial coherence method. Applying covariance subtraction yields an estimate that is obtained from a matrix where the covariance matrix of the noise is subtracted from the covariance matrix of the speech plus noise. From this resulting matrix, one is then simply extracting a column and normalizing it. Regarding covariance widening, the RTF estimate is obtained by considering the principal eigenvector of the pre-widened covariance matrix of the signal mixture. So obviously, this pre-widening, which can be, for example, accomplished via a Koleski decomposition, and also the subsequently performed eigenvalue decomposition, these operations, they come with a significantly larger computational complexity than simply extracting a column as in the covariance subtraction case. Both methods, on the other side, covariance subtraction and covariance widening, can be used with and without an external microphone. But covariance widening will yield for both cases different results. The spatial coherence method, it on the other side requires an external microphone, and it assumes also intrinsically a low coherence between the noise components and the external microphone signal and the noise components and the head-mounted microphone signals. And for a diffuse noise field where the distance between the external microphone and the head-mounted microphones is rather large, this assumption holds quite well. So, and since the coherence of the noise component is rather low, the respective column of the covariance matrix of the speech plus noise contains a rather unbiased estimate of the speech covariance matrix. So in a way where a low computational complexity is required, one can simply use this particular column as an estimate of the head-mounted RTF vector. So now, having in mind that there are these three different RTF estimation methods, which differ in their complexity and their requirement whether an estimate of the covariance matrix of the noise is used or not, or whether it depends on the availability of such an external microphone or not, these estimates should be used to ultimately retrieve the position, the DUA, of the desired target speaker. This estimated head-mounted RTF vector is compared for different discrete directions. It is compared with a database of unequal prototype head-mounted RTF vectors. And because we have only a single speaker, to make this estimate more robust, we are averaging these different distances that we obtain. And this distance metric that we incorporate here, this is the so-called emission angle. The emission angle measures the angular distance between the head-mounted RTF vector for a particular direction theta I and the estimated head-mounted RTF vector from the current estimate. So putting this all together, we want to evaluate this algorithm, and therefore we evaluate it using at recordings made in a reverberant environment with diffuse-like noise, as well as a stationary and a moving speaker. There is a binaural hearing aid setup with in total 4 microphones and 1 external microphone. All microphone signals are processed in the short-time Fourier transform domain, and the covariance matrices, they are estimated recursively and updated according to the spatial to the speech presence probability. For the static speaker scenario, different signal to noise ratios in the range plus minus 10 dB are compared in terms of their localization accuracies for different RTF estimation methods. In this figure, we see this localization accuracy for covariance subtraction, depicted in red, for covariance widening in green, when no external microphone is applied, and then also covariance widening in black for two different positions of the external microphone, as well as spatial coherence for the very same 2 external microphones in blue. Which insights do we find when we have a look at these curves? So first of all, we see that for the complete signal-to-noise ratio range, the performance of covariance widening in black and in green, as well as the performance of the spatial coherence method in blue, is better than covariance subtraction. We also find, when we look first in this non-negative SNR range, that spatial coherence localizes very similar as covariance widening. But we need to say, when we have a look on the negative SNR range, the susceptibility of the spatial coherence method with respect to the position of the external microphone, it seems to be more developed than for the covariance widening methods. Turning now to the dynamic case, where we have a moving speaker. In this scenario, the speaker is moving from minus 50 degree to plus 50 degree at a normal pace. We consider the covariance widening method, where 1 external microphone is located in the middle of the room, and similarly, the spatial coherence method at the very same position with the external microphone. The figures here show the estimated trajectory of the speaker depicted with this red line, whereas the color-coded background shows the value of the cost function, so the frequency average emission angle. On observing these results, we see, first of all, that for this trajectory, both estimation methods localize the target similarly well. So both are able to track the speaker. But we also see, so when we have a look on this region of relatively low cost function values around the estimate, so that this region is more confined for the spatial coherence estimate than for the covariance widening case, which leads to the conclusion that at least for this scenario, the localization confidence is higher when using the spatial coherence method than when using the covariance widening method. So with all these findings, I would like to conclude this presentation, and I want to wrap up. So it is well known that hearing impairment not only compromises speech communication, but also the localization ability. And to alleviate this localization deficiency, we proposed for the binaural hearing aid context a single source EUA estimation algorithm. And we also investigated how an external microphone can aid to localize a speaker in adverse acoustic conditions. We introduced the frequency averaged emission angle as a cost function for single source EUA estimation. We compared different RTF vector estimation methods in terms of their localization accuracy. And we also analyzed how exploiting the external microphone changes the RTF estimation and thus also the resulting DUA estimation accuracy. Using our experiments for a static and for a moving speaker scenario, we found that using the proposed algorithm, the speakers can be localized well in these adverse acoustic conditions. But more importantly, when we apply the spatial coherence method, which considers the external microphone, we can localize the speaker similarly well to covariance widening, but we do not need to employ algorithms with a high computational complexity. And similarly, we also do not need to estimate the covariance matrix of the noise component. This brings me now to the end of the presentation. So this is what we have achieved. And briefly as an outlook, in future work, we want to tackle not only the single source DUA estimation type, but also the multi-source DUA estimation task. We want to be able to track multiple sources in a room. And moreover, we also want to investigate how a target speaker can be jointly localized with a hearing aid user when the microphone array is not calibrated, so when there is no relative microphone information given a priori. Thank you very much for your attention, and please continue enjoying this year's EUSIPCO.